Well, shall we get started? I want to welcome all of you to the meeting today. We're starting our spring series on Wednesdays. And I want to especially thank Jeff not only for speaking first, but also while Habib is on leave, he's he's our videographer for this semester. So thank you very much, Jeff.
I didn't know Habib was on leave.
Yes. Yeah. So I want to introduce our colleague Jeff Grove from the math department, and his title today is The Universe in Color, and that's basically all I know about it, so I'll just turn it over to you, Jeff.
Thank you. Yeah, sign in. So I'm Jeff Grove, and we're going to look at today some of the most recent images posted on the NASA website about, or from, or in relation to the James Webb Space Telescope. And this is kind of a misnomer, this universe in color. The James Webb Space Telescope takes images in the infrared. And when you look at this, here it says Chandra's 25th anniversary Chandra Webb composite. So this image from the Pillars of Creation. This image is a composite from the Chandra Space Telescope and the James Webb Space Telescope. And Chandra, universe in color, remember, Chandra uses X-ray wavelengths for its images. So in what sense are we talking about color? These all have to be colorized in some way in order for them to have these colors, change the frequencies into the color spectrum. And so I suppose I shouldn't have titled this The Universe in Color. Maybe The Universe in Infrared and X-ray would be better. But this is the Pillars of Creation. And here we find James Webb Telescope finds candidates for the first candidates for young brown dwarfs outside the Milky Way in this image. So I figured this would be a good image to quote from Genesis. Here's an example of an image taken by the Hubble Space Telescope and the corresponding image taken by the James Webb Space Telescope. Remember, James Webb is taken in near infrared, and Hubble is using what, visible light? And you can see it a bit washed out in here, where you have a little bit more detail about the cluster of stars near the galactic center here. This is the Sombrero Galaxy. This image is, again, a composite image, Webb and Chandra, with everything colorized, of course, because it all looks pretty bland if you're just using the infrared and X-ray images. But this is from the Crab Nebula. Peering into the tendrils of New General Catalog 604, NASA's Webb. I think it's kind of astonishing. If you go to the NASA website, they'll have a number of different images with different versions of the color that they've put in here. They've colorized these different ways for different images.
I see snow.
You're seeing snow?
Actually, smell.
Yeah, obviously.
What is the scale here, Jeff? How big is this picture?
Well, that I don't really know. You can see it's
across.
It's going to be some light years across. It's pretty huge. This huge cloud of gas, right, is going to be fairly massive. You can see the stars within this could be many light years across. This particular image is, again, Webb Hubble. So it's a composite of a Hubble image with image as well. It looks like two galaxies that are interacting, but it also looks like maybe they're not interacting. Maybe this other one is behind this one and they're not interacting. It almost looks like if they were interacting, they would be tearing each other apart. So this, because they both look fairly still symmetrical, it looks like one is in front of the other. But this is the corresponding image from the Webb. The last one was a composite Webb in Hubble. This one's from the Webb Space Telescope. I wonder why they do all the coloration of these stars out here, but not of the two galaxies. This is actually two galaxies interacting. This is actually a smaller galaxy than this one. This is an elliptical galaxy, which these ellipticals can be quite large, on the order of 1 trillion stars. A lot of stars in these elliptical galaxies, and these others, this is a spiral on the order of 100 million stars, 100 billion stars. Looks like it's being torn apart by this other one. This is the Orion Nebula. This is a Chandra Webb composite. So if you look up at the constellation Orion down to the belt of the sword, you'll find, if you look through a good telescope, you'll see something that doesn't look anything like this. Because
So why are they these colors, did you say? Why is this?
NASA has colorized them. They've taken the various frequencies and shifted them. And that's because otherwise it would just be white and black.
But is there any scientific basis for them choosing this color as opposed to some other color?
Just shifting it along the spectrum. It's just however it is. You can shift it further or less and get different color combinations, yeah.
Correct me if I'm wrong, but aren't X-ray and infrared on opposite ends of
Yes.
Okay. So maybe the coloration comes from, yeah, measuring, finding the, mixing the two wavelengths to see where it would be in visible light or approximate.
Yeah, shift them both into the visible spectrum. Yeah. Interesting, the Orion Nebula. You see it as a little spot, a smudge in the sky, right? Usually through a telescope, a small telescope, but nonetheless. Another big nebula here, in General Catalog 3324. This is again a Chandra Webb composite. I did say universe in color, right? Maybe I should have said the universe colorized. Would have been better. You can see this galaxy being torn to shreds. It's being whipped apart. A lot of other little galaxies in the background there. I say little, each of those has on the order of 100 million stars. A lot of stars represented right there. Who knows how many civilizations existing there at this present moment. So these, if they do have civilizations, these are many, many millions, perhaps billions of light years away. So they must have been, if they are civilizations, they must have existed a billion years ago or so. And so by now, surely they're at least a billion years more advanced than us. Something interesting about this image, you see these elliptical galaxies in the foreground and these bent arcs. These are galaxies in the background. They're behind these other galaxies. And the light is being bent around these elliptical galaxies. Gravitation bends space. Light just goes as straight as it can in space, but if space is bent, it will bend. And this is one of the earliest observations from concerning Einstein's theory, the bending of light around the sun. The sun is a massive object. In 1919, Sir Arthur Eddington went out and made photographs of the sun during a solar eclipse. So the sun is blotted out. It's only during those times that you can see stars close to the sun. So you can take photographs of those stars. And 6 months later, you can take photographs of the same stars, but the sun's over here now. So at night, same stars. And you can compare their distances from how their position was changed by going around the sun. And so when the sun is there, they look a little bit further out. And that's because the light is bending around the sun. It appears like the star is over here, when in fact it's over here. Okay. And you can see that dramatically here with these bent galaxies, their light being bent around the galaxies in the foreground and being stretched out like this.
Kind of like a ray of incidence through water.
Yeah, it's being refracted. This is a gravitational refraction. When I was in high school, I was thinking, I had heard about Einstein's theory about light bending around the sun. I thought, well, couldn't it just be bending through the solar corona? Just like light going through water, right? Couldn't that be it? It wasn't until much later that I was able to do the math and realized that even if it were going through the solar corona, it wouldn't be bending as much as that gravitational refraction. So it turns out the gravitational refraction is more important, unless you're right on the solar limb, which is a little different. This is the same kind of phenomenon where you have a massive galaxy here in the foreground and a quasar in the background, with its light being bent around the galaxy in the foreground. It might not look like much, but it's kind of interesting. It looks like a ring with some stones on it. I'll show you another one of those later, maybe an illustration of what's really going on. I'll show you that in a minute. But you can see here again, this is a Webb image, the celestial fireworks around a forming star. The star forming is shooting out jets of gas through the poles as it's forming. And this is just another image of that Crab Nebula that we saw earlier, but colorized differently. So I thought I'd be honest to you and show you a different way they've colorized this. Okay.
But when they colorize something, as you say, it's not just for aesthetic purposes. There's a logic to it based on the spectrum, as you said. But are they finding structures or finding things by means of colorizing they would have missed otherwise? Like when biologists stain something on a slide.
I'll bet they do. I can't attest to that, but I'm certain that has to be true.
So, like it's green and blue,
Yeah.
were they typically, before that was colorized, was there some difference in them that caused this color to be green over here and blue there? Or was this the whim of the?
I don't think this was the whim. I think this is coming from the different infrared frequencies coming into
So
the
when
this
they
thing.
start to colorize it, it picks up certain colors here and then it changes.
Yeah, and you can shift it however far you want.
Is this the same composite image from before?
Yeah.
Okay.
So different colors aren't farther away or anything like that, or hotter or cooler?
Not on this. You'll see some later on. It's probably also colorized. I do want to talk about the red shift later on. This is the near-infrared camera, linear cam, plus Hubble this time. I think some of these are just beautiful. I like to just sit and look at these images. It's not very often I get to have them projected on a big screen like this too, so it's kind of a treat for me.
You should make that a puzzle.
Yeah. That would be cruel and unusual.
This looks like a Balrog now. And there's Gandalf.
This is also a forming star, shooting out gas, and they say the gas is moving between 45 and 60 kilometers per second away from the star. So pretty fast. It's forming a shock wave as it collides into slower moving gases, and that's what's actually creating the image here. And again, you can see the gravitational lensing, these galaxies in the background versus the galaxies in the foreground. bent like a banana, the banana galaxy.
Who's that?
It's inhabited by apes.
Galaxy of the Apes.
Yeah, that's it. That's where they got the Planet of the Apes from.
How's that for?
So here, a dying star, sort of blowing off layers of gas.
Craters in Yellowstone.
Yes, I actually have an image later on here, actually. I don't know if we'll get to it, of the Heart Spring in Yellowstone. Check that out. I think it looks like an octopus. Just phenomenal.
Christmas.
Yeah, fireworks. Celestial fireworks in this case. We'll all recognize this. Some moons of Saturn, and I don't know, you really can't see the hexagon on the North Pole here. Should get a different photo from the North Pole. It has a hexagon on there. It's very fascinating. This is infrared, right? Infrared image. So this is another one of those Einstein rings where you have a galaxy in the foreground, a galaxy in the background, where the light from the galaxy in the background is bending around the one in the foreground. And this is the explanation for what's going on. Here's the one in the background. Here's the one in the foreground. Its light is being bent around, so it looks like it's coming from over here and over here, but it's really just behind the other one.
Is that what the red dot was?
Yes, the red ring is the one in the back.
Oh, I meant the red dot over in the.
Oh, that? That's something else. I don't know what that is. I was focusing on this. I don't know. This interesting phenomenon of
I thought it was maybe an off-centered case.
No, this is the orange ring right here. And this is the galaxy in the foreground. Massive galaxy, so massive that the light bends all the way around on both sides, all sides, as illustrated here. So, called an Einstein ring.
So does it need to be the case that the galaxy in the foreground is more massive than the one in the background?
It doesn't have to be, but if it's not so massive, the light may not bend so much, and it might just pass through. So it might not be
It's
visible
a
at all.
supermassive galaxy, that's all that matters for bending the light.
If it's supermassive, there's a higher likelihood that it'll bend enough that it'll make the ring, make it visible. Something like an elliptical galaxy with a trillion stars. Not do it. So these are some of the oldest objects ever observed, most distant objects ever observed. These were observed by the Webb telescope. These are galaxies. These galaxies are close to 13.5 billion, light years away. Well, they say it could be further than that. They're expected to be 13.5 billion years old. They're going to be more than 13.5 billion light years away because the universe has been stretching all that time that the light has been in transit. This is the oldest object ever observed. Right here, it comes from this little piece of this much larger image. And it has they calculate the red shift by this formula here, observed frequency, observed wavelength minus expected wavelength over expected wavelength. And they're getting a ratio of 14.37, which is massive, it's huge. 0 would be observed equals expected, right? 0 is about what you get for in that case. But if this is where the wavelengths are really, really stretched out, that's when you get big ratios like 14.32. If you look at 14.32 over here for that ratio, Z value, that corresponds to about 13.5 billion years ago when the light was emitted. And probably much, much further than that from us now, since this universe has been expanding. So that's the little lesson on redshift that I can give you here. This is James Webb. Okay. I figured you'd want to know a little bit about the history here. He served as administrator of NASA from 61 to 68. Looks like he left 1 year too early. I don't know, he should have kept that lung working better, avoid that cancer just 1 more year. Oh well. So 1 more year and he would have been there during the moon landings. Oh. So this is the James Webb Space Telescope. And I was wondering for the longest time if they were ever going to launch that thing. They were working on it for way over a decade. So wow, that thing hasn't launched yet. But it finally was launched, and it was placed in L2 Lagrange point right here. There are, if this is the sun, this is the Earth, and this is the moon, then we have basically what we call the three-body problem. Three-body problem. In gravitational theory, even in Newton's gravitational theory, you can solve the two-body problem, but the three-body problem is really hard. Okay. And anything more than 3 is going to be really impossible. So they analyzed the three-body problem for the sun, Earth, and moon, and found that there are certain equilibrium points. So if an object is exactly at this point, assuming that we're using a rotating frame, where the frame is always looking directly at the Earth as it goes around the sun, you can use this rotating frame. So it's as though in that frame, the Earth will just stand still right here, and the moon will go around. This point right here would be an equilibrium point, but that point is an unstable equilibrium point, meaning that if you perturb off of that, you'll tend to float away from that, okay? And over the long period of time, it'll move chaotically, and there's no predicting where it'll end up. The L2 Lagrange point is also an unstable equilibrium point, as is the L3 Lagrange point. These are all unstable equilibrium points, which means the Webb telescope put into this position. Why is it here? It's put there so that it can always be observed from Earth, but it won't have interference, reflected light from the moon coming back on it. It needs to be kept very, very cold, and so it doesn't have interference from its own heat, since it's using infrared to capture these images. It needs to be kept remarkably cold, and it has a heat shield. It's very hot on one side and very cold on the other, where it collects all these images. And it stays there relative to the Earth. As the Earth goes around, it goes around. That's almost true.
Is that what you call a geosynchronous orbit?
This is way higher than a geosynchronous orbit. The geosynchronous orbit is what, 23,000 miles up? This is 1 million miles up.
Okay.
So the moon is only 240,000 miles up. This is 4 times away from the Earth than the moon is. So yeah, this is way out there, right? 1 million miles to this Lagrange point, and this one's also 1 million miles the other way. This is the place that I guess Pythagoras would have said it would be the location of the counter-Earth. If you remember Pythagorean cosmology, there's the counter-Earth. That would be in an L3 Lagrange point. And then there are 2 stable Lagrange points, but they're much further away from the Earth than this or this. There's L4 and L5. It turns out these are stable. If you look at the linearized Newtonian gravitational model, they'll have pure imaginary eigenvalues. And if you move away, the real part of the eigenvalue becomes negative, which pushes you back. If it's perturbed away from here a little bit, it'll go back. Okay. But over here, if you get perturbed away a little bit, it'll move away eventually. So since the Webb telescope isn't really at this Lagrange point, it's in what they call the halo orbit of the Lagrange point. It's in a halo orbit of the Lagrange point. I guess, do I have that picture? Yeah, right here. The halo orbit of the Lagrange point. And what's going to happen is that every 10 days to 2 weeks, it starts drifting too far away and they have to push it back into orbit with a thrust. You have to use thrusters to put it back into orbit every 10 days to 2 weeks. It's estimated to have 10 years of fuel. When it runs out of fuel, it's going to eventually go way outside of this orbit and will be useless at that point. So it's not like Hubble. Hubble didn't need anything to keep it in that orbit, other than keeping away from friction in Earth's atmosphere. But this one doesn't have to worry about that. It just has to worry about going chaotically away from this Lagrange point. Here's a numerical model of what the Webb telescope is doing as it goes around that halo orbit around the Lagrange point. So this is just a numerical model for that. So I thought I'd tell you a little bit about myself, since we're here, since I have a captive audience now. Earned my PhD from the University of California, Davis in 1995, which is some eons ago. Those are the before times for my kids. So my dissertation was on shockwave solutions of the relativistic Euler equations on non-flat spacetimes. So I allowed for spacetime to be something fixed that I can choose, and then look at the existence theory for fluid dynamics on that spacetime, allowing for shockwaves. Shockwave fluid dynamics is more difficult than smooth fluid dynamics, and so I did the shockwave case. And from I was able to prove existence from Big Bang to Big Crunch in some spacetimes. I get to choose the spacetime. I get to choose the geometry of the object I'm having fluid move on. There are some spacetimes, in particular what are called conformally flat spacetimes, where I could prove existence from Big Bang to Big Crunch. So I also looked at the case of spherical symmetry, which has its own set of problems. In the mathematical theory of shock waves, you need to keep in order to get these existence theories to go through, you need to keep the density, the natural log of the density, bounded, which means the density can't go to 0 or infinity. It has to be bounded away from 0 and infinity. So if you're dealing with a spherically symmetric, well, here's my model for the Big Bang to Big Crunch with your conformally flat spacetimes. Okay, I was able to prove these, by the way, the conformally flat spacetimes are sometimes used in intense unification, so that's one reason people study them. So I was able to prove existence of shockwave solutions from Big Bang to Big Crunch because I was able to factor out the expansion factor, which is that conformal factor for the spacetime metric, and eliminate that from the equations. So I could have the existence independent of that, which was kind of beautiful. For spherically symmetric spacetimes, again, you have to bound the density away from infinity and 0, which can be a problem because, let me show you an example here. I have fluid moving out, away from the origin. What's happening to that density as the wave moves out? Isn't the density getting smaller and smaller, like an inverse square, as it moves out? And so you have densities going to 0, which is a problem for your existence theories. Okay. Same thing if the fluid is moving in towards the origin, it's possible to have those densities blow up to infinity in finite time, which is death for these existence theories, right? So how do you fix this? My idea was, I'll just change the geometry of spacetime. What if I do this? What if I wrap my space around like this? As the wave moves away from the origin, eventually it's not decreasing anymore because it's not really getting bigger anymore. I can be a huge radius away from the origin, and since the curvature of space is such that those densities can't change anymore, I can get control of those densities. And so I thought that was a creative idea. I'll just change the geometry of space.
Jeff, how do you, when you start though at that center point and you're moving out,
Yep.
what is the impetus or the force that then causes that vector to move in a vertical?
Well,
Because why wouldn't you just continue to move out from the center?
think of it like this. My space is bent if I have a sheet of paper, something like this, and I'm constrained to live in this thing, right? What if I do this? This is still my universe, I can't leave it. But now I'm going to be going like this, right? So I'm saying that is your entire universe. There is nothing else. You're constrained to live in this object, on the surface of this object. I'm imaging it as a two-dimensional surface because I don't want to do a four-dimensional space-time. but yeah, why not make, just like on flat land, I can bend the flat space and make it curve. The square, a square who lives in flat land is still going to be constrained to live in that surface even though it's bent, and he won't be able to tell the difference. Because if I take a sheet of paper and bend it like this, a square is going to still make triangles that have angle sums equal to 180 degrees.
So do you maintain symmetry at all regions within that shape?
This will maintain a spherical symmetry
Okay.
about this origin point here. By the way, this particular model doesn't resolve the problem of fluid moving in towards the origin because you can still get density blow up at the origin. But you can imagine how you can fix that. Stretch space at the origin. Okay. So you can fix both. Okay. So after the PhD, I went and was a professor for 3 years, and then I went back to Davis for 3 years as a postdoc. And as a consequence of that, Blake Temple and I, Joel Smoller got his name on here too. Blake Temple and I proved the existence theory for the Einstein equations, the first shockwave existence theory for the Einstein equations. So this is the first time anyone's had the full dynamical interaction between the geometry of the space and the fluid moving on space that allows for shockwaves. So that's what we did. This was actually published in the Memoirs of the American Mathematical Society, which is fairly prestigious as well.
I know Smoller's name isn't on that copy.
What is that?
I know Smoller's name is not on that copy.
No, Joel Smoller is a great mathematician. He was a great mathematician. He's not dead. In fact, he obtained for me a postdoc at the University of Michigan in Ann Arbor, but I turned him down. For whatever reason, I was ready to. My wife was. She definitely didn't want me moving around from place to place. She wanted to get a job, stick to the job, and so that's what I did. So
Right,
yeah.
I have a question for you.
Yeah.
If you said you did all this research back in the mid-90s, so if you were doing that.
This was in
Not this one,
2002.
The previous one.
The one with this here?
Yes.
Yeah.
So if you were doing that today with all the observations of whatever this thing is called dark energy, and you were talking about big crunches, would you still be drawing those same conclusions?
I should mention that there's a certain problem with the observations made by the James Webb Space Telescope and the entire notion of dark energy. The so-called lambda CDM model, the cosmological constant is usually denoted by lambda, and CDM is cold dark matter. The most recent observations of the James Webb Space Telescope indicate that these galaxies, massive galaxies, were forming 13.5 billion years ago, which means it's maybe 300 million years after the formation of the universe itself. And the lambda CDM model doesn't allow for formation of massive galaxies that early.
Right.
So it's
Right.
inconsistent
Okay.
with what has been observed. So what do you believe?
The latest version of the Big Bang Theory being in crisis?
Yes, it's definitely a crisis. So who knows what
Who knows?
is going to happen. But yeah.
But does it lead to, because you don't hear much about big crunches anymore with
Right.
speaking of dark energy accelerating.
Well, that's because of the seeming the observation that the universe seems to be accelerating faster and faster apart. That was from the mid-90s. People observed that, which is entirely consistent with a model that doesn't involve dark energy or dark matter at all. In particular, just good old-fashioned general relativity. Here's the Jeff Grow cosmological model that I've been preaching since
Give it to us.
a long time. There's something called a Kerr black hole. And the Kerr black hole is supposed to be what happens when a black hole forms from a star that is rotating, which would be all of them. Okay. So, as opposed to the classical Schwarzschild black hole, which is supposed to be from a non-rotating star. There's a difference. If you're a Schwarzschild black hole formed from a star that is not rotating, the star collapses to a point. And it forms an event horizon. And any light that goes, anything that goes into the event horizon can't come out, including light. Right? And in finite time, everything inside is going to end up at the singularity and be crushed. But that's not necessarily the case with the Kerr black hole. Kerr black hole, because it's rotating, doesn't collapse to a point, it collapses to a ring. And so there's a ring singularity. And if you spend some time going around that ring singularity, you might discover something interesting, because one of the spatial variables has been converted to a second time variable. So you now have a plane of times. So you can travel through that plane of times to earlier times and come back and maybe kill yourself or play poker with yourself or pull practical jokes on yourself. But you can't go back and see Jesus Christ because he's not inside of that event horizon.
It's just you, it's only you. And
Well, you, and whoever else is inside of that black hole. You could have more people there. It might be a party, I don't know. But there's also something else that you can observe if you go a little bit further towards r equals 0 and then negative radii, which are formed at the formation of the black hole. You enter a region with negative gravity, which becomes a white hole, which repels you out into this new region that's formed at the formation of the black hole itself. And so you get this white hole side. And because of the negative gravity, the stuff that's repelled, that's sucked through there, gets repelled apart from each other at faster and faster rates because of the negative gravity. So my hypothesis is that you are in a white hole. You've always been in a white hole. Your whole life has been in a white hole. And that's the reason why the universe seems to be expanding at an accelerating rate. It's that we're in the negative gravity side of the Kerr black hole.
Wow.
Okay.
Okay.
So when's it gonna just all blow up someday? If it keeps
Well,
expanding?
yeah, we'll end up with the thermal death of the universe, right? Isn't that what they say? When things get spread further and further apart, the energy is thinner and thinner, it's going to get colder and colder, and eventually it's the thermal death of the entire universe.
So complicated.
Yes.
And yeah, and if it gets to be that cold, it may cease to exist in certain ways. I don't know. So, yeah, here's the a model for an expanding universe, but one that's expanding at a slower and slower rate. I've had time going this way, the size of the universe getting bigger and bigger as we go out. These are your spatial cross sections at different times. As the universe is stretching and getting bigger and bigger. So this is a model for the classical Friedman-Robertson-Walker Big Bang model. These would be time vector fields, by the way. These are little time arrows of time. They point in the direction that you should go. They're tangent always to the universe. They're tangent to the surface of the universe here. And so they point in the direction of increasing time. But if you look at these from the bottom end of this elliptic paraboloid here, you'll find that these all time vectors are pointing out. And what you can see what happens to the time vectors as you move forward in time. They're still going to be just tangent to the universe like this. But what happens if you move back? If you move back, you get to a point where the vector field has an infinite divergence. It has this singularity in the divergence of this vector field. You can't extend the time any further back. Which means, what does it mean to be before that time? There's no time before that because the time vector field cannot be extended before that. So all space, time, and matter came into existence at this point in time.
So it looks like to me.
Right. So before the Big Bang, what do you mean before the Big Bang? There is no before the Big Bang, right? There's no before. There's no concept of before because time is tied to the universe itself, and those vector fields can't be extended any further.
This side of the electron, there's not.
Wait, say that again.
Unless you're in the Kerr black hole model of the universe. Yeah. In the Jeff Grove cosmology that I mentioned earlier, maybe we came from a larger universe. It's possible, but then again, where did it come from?
There you go.
Hawking's singularity theorem, back from the 1960s, says that if gravity attracts on average, it's a pretty generous assumption, if it doesn't always attract, but it attracts on average. If the universe is currently expanding, then there must have been a space-time singularity in the past.
He got that from Lemaitre, who told that to Einstein, so, yes.
Oh, you're saying he copped that off these other guys, huh?
Yes, he did, but that's what scientists do. So.
But didn't he prove it, whereas the other guys didn't? See, the first proof was
Did
to
he?
Hawking, yeah.
Did he prove it?
Yes. This is proven.
Fascinating.
Oh, you don't believe it's proven?
Okay.
That's a mathematical theorem, okay.
Yes, it was a mathematical theorem, there you go.
Indeed, and it was proven by Stephen Hawking. That's my experience of it.
So it's the theoretical physics versus the experimental physics, right?
Yeah, when it comes to that.
I get you.
Yeah, our mathematics is used for making models.
Agreed.
Right? It's used to make a lot of models that don't exist.
Understood.
And who knows if any of our models exist? That's your point, I suppose, right? Okay.
Not trying to be a naysayer, because there's plenty of evidence to show some of these other things, so, right, so
Yeah.
I'm not a destructor.
So we're never going to be able to see any event before the thermal condensation of matter event in the past. We won't be able to see it because light couldn't transit the universe before that point. So there's a time limit. You can't see anything earlier than that. There's nothing that you can see earlier than that point in time. We haven't really, that's almost true.
But Jeff, could I ask a question, and I'm so sorry
Yeah.
to interrupt you, but light, so photons are made up of pure energy, they
Yeah.
are not made up of mass. So
Right.
when you're talking about all
Zero.
matter, energy, yes, space-time, does it make a difference whether or not we're talking about energy or matter, especially if you can go equals mc squared and you can convert,
Yeah.
right?
Mass, energy, and momentum are all codified into the mass, energy, momentum tensor. And so, even light. So, there's a barrier beyond which light observations are impossible, but we can detect gravity waves from before that time.
Listen.
There you are.
Yes.
So that's the one holdout yet, though nothing's been observed at this point, right? So,
Got our parallel universes at that point?
well, not necessarily. Who knows about parallel universes? These are non-scientific concepts. I don't know. I can't. Yeah. There is microwave background radiation that shows the universe was much more highly condensed in the past than we observe now. So I wanted to, if we have time, maybe I should just stop here and give you see if you have other questions, or I don't know. I was going to talk about give you some other photos, maybe. I'd like to see some of these. This is obviously the Orion constellation. You have your belt here and your sword, your juice.
I did have a question about just the photographs, or the Webb images. My favorite Hubble image ever is the ultra deep field.
Oh yeah, I
Which
love that
one?
one so much.
The Hubble ultra deep field, where they stared at what appeared to be a blank space, a piece of sky.
Yes.
just full.
Filled with galaxies.
So I wonder if they've done anything similar to that with Webb?
Yes.
They have?
Yes.
And what did that look like?
Very similar.
Very similar.
Yeah.
Just pick an empty spot of sky and it's full of stuff.
Do you see the teapot?
Short and stout.
Yes.
You see, you can see anything you want
Yeah.
in these constellations, right? You can impose your particular biases and interpretations on these things that you observe. Do you see the dragon?
I do.
This is a photograph that I took myself.
Where was
Here's
this?
the dragon.
Arches National Park in Utah.
In Utah, yeah.
Where you
You see the buzzard up there?
Oh, wow.
That's
what I
right.
see.
Where's the dragon?
There's the mouth, there's the nose, there's the eyebrow ridge, there's the eye.
Oh, right.
You see it now?
It's-
You can't unsee it now.
Right.
Yeah. Where'd the buzzard go?
The buzzard, man, way at the top, that looked like God.
Now, did I see the dragon?
But we're imposing this on a natural thing, natural formation in the desert, right? What do you see here? Is there any interpretation that we have of this? Are we imposing our interpretation on this?
Yeah.
This is obviously a natural formation in Utah, an Arches National Park.
Was it underwater?
What's that?
Was that underwater?
No. It's sitting up there, right? Oh, you mean, was it
At one
formed by
time.
water flowing around here? I don't know, over a period of time. Well, I can tell that this was definitely made by people, right?
I feel like I'm
That's
seeing
3
something.
surveyors and some other guy.
There you go. Nice.
This is by me. I took this photo.
Surveyor General.
I took this photo too. You recognize this?
I do see this tower in my home.
Attracts people from all over. Attracted me from off the highway to go see it, right?
That was a tough one to climb.
I didn't climb it. I wish I had climbed it, but I was there with my kids. I had
Lame
little kids.
kids.
Yeah. See, there's my son.
Aw.
He's being eaten by a dragon, by a dinosaur. Oh, and there's some of those geysers out in Yellowstone. And obviously, Old Faithful here. You see that heart spring?
Yes.
A lot of eye candy for you here. Another photo that I took by the Grand Canyon. I dragged my poor kids and wife all over the place. There they are, my wife and kids, standing next to this smelly, sulfurous, bubbling cauldron of gook. That's also Yellowstone, of course. Took them to, you recognize where this is? It's out in Kennedy Space Center.
Florida.
Yeah, it's in Florida. So what is Cosmo? I don't know, should we see if we can find any more pictures in here? Ah, yes, this is the ancients' picture of the universe, their cosmological view. Is that there's a firmament, which is a shell over the sky, and it has floodgates, and God can open the floodgates and water can come through, and that's how you get rain. Okay. And the earth is standing on these pillars.
There's the children's model.
So that's a pretty ancient model. This is where the Earth is, a round disk surrounded by river Oceanus, divided in the middle by the Mediterranean and Black Seas. The sky arches above the Earth, and their offspring, the sky and the Earth are actually gods that have offspring. Okay. We're many gods. So Prometheus made creatures of mud, and Epimetheus gave them skills, abilities, and protection, though he ran out of gifts just before Prometheus made humans. So we didn't get any gifts.
I really don't envy Atlas when you take into account all the Greek mythology. His whole job is basically to prevent his mom and his dad from boinking his mom. That's his punishment.
Exactly. Thales or Thales, one of the 7 sages of antiquity, he said all comes from water. And that's because over the course of his lifetime, he had seen the beachfront progress 1,000 feet out into the Mediterranean because of the silt coming from a river. So land comes from water. Right? And earthquakes are caused by the fact that the earth is floating on a sea, and when the sea undulates like this, it might cause the earth to bend and cause earthquakes. So he had a naturalistic explanation for earthquakes. Yes?
Back in the beginning, you showed how they judge how old galaxies are, like one of them was 14 trillion or something. How's that compared to our galaxy?
Our galaxy?
Yeah.
How old is our galaxy?
Yeah.
I don't know how old it is. I just know that it's pretty far across, at least, what, 100,000 light years across?
I have no idea.
So the Earth has gone many times around in the course of its history, right? 4.5 billion years, the Earth has been here. How long has our galaxy been here? I don't know.
Well, is it young, old compared to some of these others, or?
It could be just as old.
You had that scale that showed 14 point something with the lines.
That was, that's how long the light has been in transit from there to here. That's 13.5 billion years. So, yeah, the light that we're observing is 13.5 billion years old, which means since the universe is only 13.7, 13.8 billion years, that those galaxies must have formed about 300,000 years after the formation of the universe itself. So that's the remarkable thing. How could a galaxy that big form so fast? Big enough that we can see it, even though it's 13.5, it's more than 13.5 billion light away.
According to AI,
Yep.
the Milky Way is 13.61 billion years.
So they're saying it formed about,
At the same time?
Our
yeah,
universe is about 13.8 billion,
that's what they say.
It's on NASA.
according to AI.
Right.
And NASA.
Yeah, NASA, it is. It does say NASA Space Force.
So a lot of this all happened at the same time, it
A
sounds
little
like.
over, a little under 4.
Thales gave the first mathematical proof. Pythagoras, whole number is the basic element of existence. If you study anything deeply enough, it comes down to a consideration of ratios between whole numbers or proportions of whole numbers. So everything is ultimately reduced to proportions of whole numbers, fractions. The Earth is a sphere, which, along with 5 planets, Sun, Moon, counter Earth, and sphere of stars, revolve about a central fire. So he's making a logical disconnect between the sun and day and night. Day and night comes from the central fire. The sun's different from that, not causal. So, kind of fascinating. Orbits have proportional radii for these various objects, so that these are all in crystal spheres. If you ding those crystal spheres, they'll make a harmony. You have the harmony of the sphere. They have to be these nice proportions. He invented, by the way, the musical scale, right? By making proportions of a string. And so he's getting at that harmony of the spheres. So Aristotle, 4 elements.
5.
You say 5?
Ether. It's
Ether.
explicitly mentioned in the physics.
So all objects have a natural type of motion. Straight lines are still or circular motion, not the result of the influence of one object upon another. Heavenly objects are perfect, and so they have exactly circular motion. Okay. And spherical shape, because they're perfect. The Earth is central to the cosmos, the perfect planets orbit the imperfect world. Outermost sphere of fixed stars, beyond which is the spiritual realm of Ptolemy with his epicycles. St. Augustine, Earth is rectangular, has a big dark sheet stretched over it. At night, the angels place the stars on the sheet. Of course, you have Copernicus with his observations indicating that the planets and the Earth orbit the sun. And then, do you see this? It's Jupiter with its Jovian moon, with the Galilean moons. Yeah, so that's what Galileo was looking at through his telescope way back.
Did you take that photo?
This one I did not.
Galileo did.
Yeah.
But yeah, so you can see these. It's fascinating, these moons right there.
And we're gonna go explore Europa. It's coming.
Kepler,
Enceladus.
Newton. I want to talk about problems with Newtonian cosmology.
Oh, yes.
Here you have Mercury, it's orbiting the sun. This is the sun. Mercury's orbiting the sun. Now, if you believe in Newton, planets are supposed to move in these nice ellipses, right? But as a matter of fact, Mercury gets pulled out of that nice ellipse by the gravitational attraction of all the other planets in the solar system. But there was a French astronomer, Leverrier, who calculated the effect of all those planets on Mercury, and there was a small defect left over. A small defect where the perihelion of Mercury would advance this way about the sun with each orbit. So it would go more like what we're seeing here. This is hugely exaggerated, by the way. The effect that was observed by Leverrier amounts to 43 seconds of angle per 100 Earth years. And since Mercury orbits the sun about every 3 months, we're talking about 400 orbits of Mercury ends up 43 seconds of angle. It's a very, very fine thing, right? But it can be measured. And by the way, Leverrier discovered Neptune by pencil and paper.
Wow.
Because of the perturbations of Uranus, he was able to say there must be an object pulling Uranus out of its orbit,
Yeah.
and he calculated where it must be, and he told other astronomers to look here at a particular time, and they found Neptune. So he found it by pencil and paper. So, so planets according to Kepler. Here's that huge exaggeration of the advance in perihelion of Mercury as it goes around. Huge exaggeration.
Looks like a flower.
Yeah. It'd have a lot more petals there.
Yeah, that's it. That's it.
Here's the perihelion is the closest point. This is what it does. This is 1 degree. 1 degree. And 1 degree is divided up into 60 minutes of angle. And if you're on a rifle range at 100 yards and you shoot towards a target at 100 yards and you miss it by 1 inch, you've missed it by 1 minute of angle. That's 1 minute of angle off if you miss the target at 100 yards by 1 inch. For me, I'm usually missing it by, what, 4 inches? My rifle's supposed to have, 0.75 minute of angle accuracy, but then again, they didn't anticipate me. So you can imagine 1/60th of that, 1 second of angle, is 1/60th of an inch at 100 yards. Okay, and we're talking about 43 seconds of angle, so it's getting up there. 43 seconds of angle every 100 Earth years. But it does affect when Mercury transits the sun. Here's the sun, here's Mercury. By several seconds each orbit, and over a number of orbits by several minutes. And so it was well within the observational errors of Leverrier in the 1840s, 1850s. Well within observational error. So astonishing that he knew about this unaccountable 43 seconds of angle advance in Mercury's perihelion. He had accounted for all the rest of it. So, of course, he hypothesized the existence of another planet, and it had to be very close to the sun because no one had ever seen it. You have to look right at the sun to see it. Okay, so, and since it's so close to the sun, it must be really hot, so you call it Vulcan, of course. Right? And so, there were careful searches, and after all those years, this remained an open problem for 57 years. And then came Einstein. Okay. And he said, well, it's not that there's another object pulling Mercury out of its orbit, it's that you have the theory of gravity wrong. And in his 1916 paper, he accounts for exactly that 43 seconds of angle in the advance of Mercury's perihelion using his theory of gravity, Einstein's general theory of relativity. So in that one paper, he overthrows Newton's theory of gravity. Einstein's theory does a better job accounting for what we observe in our own solar system. Okay. So, maybe we should stop here.
Yes.
The Andromeda Galaxy.
Yes.
Does anyone have any final questions? Well, thank you so much, Jeff. Please help yourself to refreshments, and if you haven't already, would you please sign as you leave? And next week, Marvin Hobson from the English department is speaking on something he's a great expert on, the ethnography of Zora Neale Hurston, Haitian voodoo and zombification.
Nice.
Mathematician.
Mm.
So,
That's
as
what's
you
wrong with me.
speak, there's a creativity that needs to be there. So.